All right, back to actual lectures. So I'm going to skip derived rules 10 and 11 and let you read about those. And here we're going to look at derived rule 12 together. So this one is called alternative eliminated. And hopefully you can see why. So this rule says that, well, it's an implication. So it's saying, if you ever manage to prove this, then you can deduce this. So it's saying, if you've got phi or psi, and you've got not phi, then it must be psi. So if either phi is true or psi is true, and one of the alternatives is eliminated, you manage to eliminate that phi is true, so you know that not phi, then you can deduce that psi must be true. So hopefully that sounds reasonable. And it's tempting to just say, well, that's just what is meant by or and not. That seems like it should just be logical. Like, why do we need to write anything? Well, but of course we want to derive it from only the rules that we've given so far. So far, if we want to use an or to prove anything, all we've got available to us basically is proof by cases. So what I'm referring to is this position in the table here. If I want to use a disjunction statement, if I want to use an or, basically I have to do a proof by cases. And that's the fundamental rule for how proving an or works. Sorry, I think I misspoke. That's the fundamental rule for how you can use an or. And here, this derived rule is giving us another way to possibly use an or. Once we've established this, then you'll have another way to use an or, which is to eliminate one of the alternatives. Then you can deduce the other one. All right, so to prove this, what am I trying to prove? An implication. So I must assume the hypothesis and then prove the conclusion. So assume that phi or psi and that not phi. And I mentioned in the previous lecture that although there's technically a distinction between assume that phi or psi, wedge not phi, and assume that phi or psi, and then go ahead and assume that not phi, we're not really making that distinction. So whether we view them as two separate assumptions or not, let's just not care about that. Just for the sake of saving some words. So these are our assumptions. Then we'd like to prove psi. That's our goal, is now to prove psi. So how can we do that? Well, all we've got to work with is this not phi, which I don't know what to do with that, and this phi or psi. Well, with phi or psi, there is a way to use that, and that's proof by cases. So I can say case 1, suppose that, so I know that either phi or psi is true. So in the case that phi is true, let me see if I can fill this in and complete the proof. And then in the case that psi is true, let me see if I can fill this in and complete the proof. So let's see if this works. Well, case 2 is pretty easy because psi is actually what we're trying to prove. So it's done already. If you suppose that psi is true, then that's it. We are done. On the other hand, case 1 is going to take some effort. So I hope that after my argument, after everything's said and done, I can deduce psi. That's the hope. Well, here I have phi, but remember I also have not phi. So it looks like we have a contradiction, right? Then phi and not phi. A contradiction. Now, bear in mind, this was not a proof by contradiction. We were not trying to prove something by contradiction here. This is just one of the cases one of the two cases in a proof by cases. But we haven't broken mathematics or anything like that because the contradiction arose only in one case. So all it's saying basically is that that case is an impossible case. But to really finish, technically, we have to reach the end in both cases. So in case 2, we reached the end, psi. In case 1, I also want to eventually reach psi. But as soon as I reach a contradiction, then I can do it just because of this rule. Because of this rule from before, that if you have a contradiction, then you can deduce anything you want from that. So here, then we can deduce anything we want. So let's just deduce psi. That's the thing I choose to deduce. And now we're done in both cases. So that's derived rule 12. And now when you're faced with an OR that you have, when you know that an OR statement is true, you have another way to possibly make use of it, which is to eliminate one of the two sides. Then you'll know the other side is true. So we just covered derived rule 12, and I will let you read derived rule 13 on your own, and for the next one I'll skip ahead. And in the next video we'll talk about contraposition and prove derived rule 14 together.